Let's talk about section 6.7, which discusses the concept of compound interest. All right, now the first type of interest that you typically see is what's called simple interest. And this is not compound interest. But I wanted to talk to you about this for a second because it connects to the idea of compound interest. Now with simple interest, the idea here is that I'm going to have what we call a principal of P dollars. So that's like the investment, right? My beginning or initial amount of money. I'm going to borrow that money for T years, and we're going to apply an interest rate basically one time per year. All right. So we can say that the interest that I earn, this is called the simple interest formula. The interest that I earn is I'm going to have my initial investment, my principal, times my rate of my investment, and we're always going to write that as a decimal, and then times the time in years, T. So a real quick illustration of this idea of simple interest is the following, right? So it says a credit union pays simple interest of 4% on a certain savings plan. So if $2,000, that's my principal, right, is deposited into that plan, and how much will the account have after 5 years? So if we're going to do the simple interest, we're going to apply that simple interest formula. We're going to basically say our principal is $2,000, our rate was 4%, and our time of our investment was 5 years. And this is called the simple interest. So again, I'm going to apply that 4% rate at the end of each year, and the interest that I'm going to earn is $400. Okay? So I would then take that $400 as my interest and add it back into the account, and I now have $2,400 in my account. Now, this last step is actually kind of the idea that we'll talk about in just a second, called compounded interest. Now, what I want to point out to you here is that if I calculate 4% of $2,000, that would be $80, right? Let me pull up my calculator here and show you, right? 4% of $2,000 is $80. So basically what's happening here, my interest is not compounding. I'm just earning $80 at the end of each year. So over the life of the 5 years, I get the $400 in interest. Now what's interesting about compound interest is we're going to actually add the money back into the account before I calculate the next cycle of interest. Let's see what that means. So first of all, I want to point out to you that when we talk about different terms of applying interest, or typically what we'll see is annual interest, that's once a year, semi-annual is twice a year, quarterly, 4 times a year, monthly, 12 times a year, daily, 365 times a year, so on and so forth, right? So we're going to talk about compound interest. We might see some of these terms. I just want to point out to you, right, what that means. If we compound quarterly, that means we compound 4 times per year. So in this example, let's suppose that a credit union pays that same interest rate of 4%, and we're going to compound quarterly. And if $2,000 is invested in the plan, right, how much is left in the account after 1 year? Right? So if we were going to do this the long way, I just want to show you what compounding really means here. If we're going to do this the long way, what we're going to do is we're going to break the year into 4 pieces because we're compounding quarterly. So in the first quarter, we're going to earn 4%. And that's that $80 that we talked about. So I'm going to take my 4% of I'm actually breaking the rate into a quarter. So I'm going to take the 4%, break into a quarter, and I'm going to apply that at the end of the first 3 months, and that's going to give me the $20, right? Now here's where things change. So here's what compounding means. So the compounding means I'm going to take that $20, I'm going to add it back into my account. So now I have 2020. So the 2020 is going to earn interest in the next quarter. Now obviously that's going to be a little bit more than $20 because my account is now 2020. So 2000 earned $20. 2020 is going to earn, excuse me, a little bit more than $20. You see, that's going to be $20.20. Right? So at the end of the second quarter, I take my 4%, I've divided it into 4 quarters, and that is how much I'll have at the end of the second quarter. So at the end of half of a year, I now have the 2020 from the prior quarter plus my new amount of interest. I now have $2,040.20. So in the third quarter, this is now the amount that is going to earn money. So at the end of the third quarter, I'm going to earn $20 and basically 40 cents, right? So I'm going to add that back into my prior amount. Here was my prior amount from the end of the second quarter. I'm going to add my new amount of interest. I now have $2,060.40. So just to finish this problem here, right, we got one more quarter. I'm going to take this amount and it's going to earn interest in the last quarter. That's going to earn me $20.61 in essence if I were to round. So I'm going to take my new interest, add it into my account, and this is the final value I have in my account at the end of the 1 year. $2,080, and it looks like this would round to 1 cent. So this is not really what I want to do when I'm asked to compound interest. We have a formula that's going to do that for us. But I just wanted to show you where this concept comes from. What does it mean to compound? So if we just kind of come back and look at this example one more time real quick, and I just want to talk about the pattern that we might notice here. So in that example at the end of the first quarter, what we had was the $2,000 plus the 20. So basically what we ended up with was the following. We have $2,000 plus, here's where the $20 came from, right? It was the quarter of the 4% interest. And I could literally factor out this 2,000. If I factor that 2,000 out, I end up with 1 from this number and 0.04 over 4 from that number. So this is actually how I could find the value at the end of the first quarter. Now, in terms of a formula, right, here's the formula we're looking at. We have our principal times 1 plus our rate over the number of compoundings per year. That's what we really have here. Our principal, 1 plus our rate, our 4%, over the quarterly, right, the n compoundings per year. So as a formula, this is what we're looking at there. Now, if we were to look at this a little bit deeper, and again, I don't want to dwell on this too much, okay? But if we were to look at this a little bit deeper, look down here. Here's what we're going to have at the end of the second quarter. So we're going to have the 1 plus r over n actually appear twice. And we're going to get the square term right here. So at the end of 2 quarters, we get the square term here. At the end of 3 compounding periods, we're going to get this term cubed. At the end of 4 compounding periods, we're going to get this term to the 4th power. And so the formula that we have in this section for what we call the compound interest formula, we're going to literally have 1 plus r over n term n times, right? And then we're going to multiply by the number of t years that we are investing for. So this is our compound interest formula. We don't want to have to do what we did in the prior example to compound the interest. This formula is a shortcut that shows me or provides that value for me at the end of all of those compounding. All right, so let's take a look at a different example where we would apply that formula a couple more times. So in this example, we're going to suppose that we have a principal of $2,000. We're investing at a rate of 8%. So letter A says, find the amount that would result if we compound quarterly for 10 years. All right, so for letter A, we're using the compound interest formula. And because we're compounding quarterly, the n is going to be 4 here. Okay? We're compounding for 10 years, so the t is going to be 10 here. And then our principal, right, our initial investment is 2,000. That's my p value here. So if I plug all of that into that formula, and then I take out my calculator and crunch that value, I'm going to get $4,416.08. So again, this is the accumulated amount at the end of the 10 years. This is how much I have collectively, interest and my principal investment. All right, and then just a word, note here on the calculator. If I'm using a TI, this is actually pretty easy. I'm going to type 2,000, put parentheses. I'm going to literally type it just how I see it. 1 plus 0.08 divide by 4. And I'm going to raise to the power, let's see, 4 times 10 is 40. And when I hit enter, there's that value that we get there. Now, if I'm going to use, let's say, a scientific calculator, I got to be a little bit more careful. I got to do things according to orders of operations. So if I'm going to do things according to order of operations, first I'm going to work inside the parentheses. I'm going to find 0.08 divided by 4. and hit equals. And then I'm going to add 1 to that. So I'm going to say plus 1 and hit equals. And then I'm going to raise that to the 40th power. So I'm going to hit the X to the Y button and raise it to the 40th power and hit equals. And then I'm going to multiply by 2,000. So I'm going to do times 2,000 and hit equals, and there's that same value. So depending on the type of calculator you're using, you just got to be, follow your order of operations. If you're using scientific, or if you're using a TI, you just type it in how you see it, and it'll give you the result there. All right, now let's take a look at letter B. So letter B says find the accumulated amount if we compound monthly for 7 years. So again, if we compound monthly, that's n equals 12 times per year. So both of these n's are going to be 12. I'm doing this for 7 years, so my t will be 7. My rate was 8%, so that'll be 0.08. And then my principal was the same, $2,000. So plugging in all those numbers and then using whatever calculator I wish, that would give me an accumulated value of $3,494.84. So that's what it would look like to apply this compound interest formula. Again, we don't want to do what we did on that first example. We don't want to have to actually do every single compounding. This is a nice shortcut to give us the final accumulated amount. Now, in this example, the objective here is just to do some comparisons. So notice it says we're going to compare investments using different compounding periods. So for this example, we're going to invest $1,000 at a rate of 10%. And what we're going to do is look at what happens if we take that $1,000 at 10%, we compound annually, we compound semi-annually, we compound quarterly, monthly, and daily. Right? What would we get at the end of 1 year in each of those scenarios? So I'm going to use my compound formula, right? And again, my principal is going to be 1,000. My interest rate is going to be 10%, so I'm going to write that as 0.10. And in each case, if I compound annually, n is 1. Right? If I compound semi-annually, n is 2. If I compound quarterly, n is 4. Compound monthly, n is 12. Compound daily, n is 365. And then for all of these problems, it's just looking at 1 year. So I'm going to let t equal 1. So annual compounding, I'm going to end up with $1,100. The semi-annual compounding, I'm going to end up with $1,102.50. With the quarterly compounding, I'm going to end up with $1,103.81. With the monthly compounding, I'm going to end up with $1,104.71. And with the daily, I'm going to end up with $1,105.16. All right, now, hopefully this is kind of intuitive, right? Obviously, within, let's say, a fixed time frame, right? We fix this to 1 year. The more that I compound, the more that I'm going to earn, right? That doesn't grow, it doesn't get as big as you might think, right? I mean, you might think that if I compound every day of the year, I'm going to get a lot more than compounding only 12 times a year. And as you can see, it's not that big of a difference, right? I mean, it is an increase, but it's not that big of a difference. All right, now the next concept in this section is what we call continuous compounding. So continuous compounding is what if I compounded infinitely many times throughout the year? And again, that's not very realistic, right? However, think about this, right? If I compound quarterly or I compound monthly, I compound daily. What if I compound every hour? What if I compound every second? What if I compound every half of a second, right? So if I could let my compoundings become infinite, what would that do to my money? And what's really interesting here is that actually brings about the number E. And before we look at the number E coming into this, I just want to show you on Desmos real quick. Here's the compound interest formula. Excuse me. And with my compound interest formula, I just plugged in a principal of $1. I used 10% interest, and I compounded quarterly 4 times a year. And then I'm just letting the time be variable here. And you can notice that as time increases, my money is exponential in behavior. Right? So when I graph this compound interest formula, as time grows, my money grows exponentially. So it should be no surprise then when I think about letting my compounds get bigger, this is also going to be exponential growth. Now, I'll remind you, we looked at this really quick in 6.3 when it talks about exponentials. But here's the definition of the number e. This was shown to you in 6.3. We talked about it briefly, right? I just want to point out to you that if I do the compound, here's my compound formula. I can do a little bit of algebraic magic. And what I can do is like reverse flip and multiply this expression and write it as 1 over n over r. Right? And what that does is allows me then to connect to this formula here. Because in essence, I can multiply outside that exponential and I can create this expression. Right? So with a little bit of creative algebraic manipulation, my compound formula can be manipulated to look like a base e exponential. So that's actually what happens as the compoundings become more and more and more and more, as they become infinite, I end up with the base e exponential. Again, here's just a table of data reminding you that this number right here is the number e, 2.718. There's my number e. So when I let compoundings become continuous, the formula changes to a base e exponential. And some students I've heard joke around and call this the PERT formula, right? So here we have p e to the rt. So if I'm compounding continuously, notice the n, number of compoundings per year, totally missing in this formula. All we need is the principal, we need the rate, and the time. We don't have the n in our formula anymore. Right, so again, back on this slide, this was the compound interest formula, in which we have the e in that formula. Excuse me, we have the n value in that formula, the number of compoundings per year. But if n becomes infinite, we compound continuously, this turns into an e. We get e to the rt. I'm curious if the formula, I just thought of this, I don't know what made me think of this, maybe because it's been a long day. If this formula is called the PERT formula, what on earth do you call this formula? Or how would you say Pawarnt? There we go. That's the Pawarnt formula. I like that. All right. So we got the PERT formula is our continuous compounding, and we got the Pawarnt formula. That's really silly. All right, forget I said that. That would be our compound formula. So this is a little funny, right? So when we say compound interest, we're meaning compounding n times per year. And when we say continuously compounding interest, we're meaning n is infinite when we have our PERT formula. So let's take a look at an example where we would apply the continuous compounding idea. So in this example, it says find the amount that results from investing a principal of $2,000 if we compound continuously. So suppose letter A, we compound at a rate of 8% for 10 years. So again, my principal is going to be $2,000. My rate is 8%, so I'll write that as 0.08, and my time is 10 years. So I plug that information in, and then that would give me $4,451.08. All right, now again, if I'm using a TI calculator of some sort, I'm going to type this in just how I see it. I'm going to type 2,000, and then I need the E, so I'm going to do second ln. I'm going to bring up the E, and I have 0.08 times 10, and then I'll close the exponent, and there's the value that I would get there. All right, now in the second example, we have 5.5%, so I'm going to write that as 0.055, and we're investing for 20 years. And then if I plug that into my calculator, I'm going to get about $6,008.33. All right, now the real excitement here is when we leave the time or the interest rate as the variable, because then we're solving an exponential equation where our unknown is in the exponent. So we're going to take a look at a couple of examples in just a minute. Before we do that, let's take a look at one more example called finding the present value. So basically what the present value is asking you how much do you invest now so that you'll have a certain amount in, let's say, 10 years or 20 years. So in this example, they talk about a zero coupon bond, and it can be redeemed in 10 years for $1,000. So it says how much should you be willing to pay now if you want a return of 7% compounded monthly or 6% compounded continuously. So if I'm compounding monthly, again, the idea here is that in 10 years, I want $1,000, right? So I'm plugging $1,000 into my compound formula. I'm plugging 10 into the time. And we're being told we're compounding monthly. So I'm plugging 12 in for the n, and here's our 7%. So I'm finding what we call, this is the present value, right? This is how much money I'm willing to invest today so that in 10 years I end up with $1,000. Now, this is not solving an exponential equation because I don't have variables in the exponent, right? I just have the variable right here. So literally all of this stuff right here is just some decimal value. I'm going to divide it over to the other side, and then the 1,000 divided by that number is my present value. So if I take out a calculator and crunch that number, I get $497.60. So I should be willing to pay $497.60 in order to have $1,000 in 10 years if we compound 7% monthly. And then if I do letter B, I'm doing the continuous compounding, right? So now I'm using the PERT formula. So now I want $1,000 after 10 years at my 6% as stated in letter B, and I'm finding this principal value. So again, this is just some decimal number in my calculator. I'm going to divide it over to the other side. So I take the 1,000 times the e to the negative 0.6, and that gives me the 548.81. So that's my present value, how much I'd be willing to invest now to have $1,000 in 10 years if we compound continuously at 6%. All right, now let's look at the really interesting problems that I was talking about. So if we're looking for the rate or the time, this is an exponential equation that we're going to solve. So this first example says, what annual rate of interest, if we compound quarterly, should you seek if you want to double your investment in 6 years? All right, so again, since we're compounding quarterly, I'm going to use my compound interest formula and plug in everything that I know. Now, I don't know how much I'm investing, but I know that whatever I'm investing, it's doubling in 6 years, right? So I just assumed it was $100, and I doubled that to $200. Right? I left the R alone, and I put the N of compound quarterly, and then this is 4 times 6. Right? Remember, I have N times T, and I'm solving for that R value. Now, in this particular case, I'm going to divide both sides by 100 first to isolate this term over here, and that gives me 2 equals that term. And then all of this stuff is raised to the 24th power. So I'm going to square root, or I guess it's going to actually be 24th root the right-hand side, and I'm going to 24th root the left-hand side. Then I'll go ahead and subtract the 1 over, and then I'll multiply both sides by 4. And if I take out my calculator, that tells me about 11.7% would be the rate that I should seek if I want to double my money in 6 years, being compounded quarterly. Now let's take a look at another example. In this example, letter A says, how long will it take for an investment to double if it earns 6% compounded continuously? So in this case, we're compounding continuously. We're going to use our PERT formula. So again, I'm going to plug in what I have. I'm going to assume I invested 100. I'm going to double it to 200. And then here's my rate of 6%, and I'm finding the time that that would take. So again, I'm going to isolate the exponential. I'm going to divide the 100 to the other side. And then now I'm going to have to log both sides of this equation. So I'm going to ln the left-hand side. I'm going to ln the right-hand side. And as it turns out, these are inverses of each other, right? This is log base e. This is a base e exponential. So those wipe each other out, and I get just the exponent. And then now I'll divide both sides by the coefficient of t. And there's the time that it would take. About 11.6 years is how that would take. And letter B says, how long will it take to triple at this rate? So if I'm assuming I invest 100, that triples to 300. And again, I'll take the same exact process. Divide both sides by 100 to isolate the exponential. Then I'm going to ln both sides of the equation. Again, in this case, these are inverses and undo each other. And then I can isolate the t. And I get 18.3 years that it would take to triple my investment. All right, so that's, I think, everything I want to look at here in 6.7. So as always, if you guys have any questions, please post on the discussion board on Blackboard, and I will see you in our next video.